There we go. Okay. So last week, right, we talked about section 44, 45, 46. We'll actually continue some of 46 today. In fact, I'd be perfectly fine. I mean, tell me if you guys like if you guys want me to do something different. But I think I might just go through the rest of kind of like 46 and we'll see if we get into 47, which is convolution. Just quick thumbs up. Has everyone at least been to the study group or watched the study group from last time, which would have been section 46? Give me a thumbs up if you guys, I see a nod. I know some people were actually in the study group. Okay, see some thumbs down. That's okay. Has everyone gone through at least like seeing the first part, which is I think either in study group for section 44, 45, where we start introducing neural networks? Yeah, I see a little, that's okay. I see a little head shake too. But I think most people had gone through. So is where I'll suggest like definitely go through. I'm taking more time for neural networks because these are the things that will really, what's it called? Like stack on top of each other of deep learning in general. Is that knowing deep learning, knowing neural networks will make it easier to understand newer concepts in deep learning. And there are new strategies, algorithms, kind of architectures of deep learning and applications of deep learning that if you understand the first part, it'll be a lot easier to understand what's going on to begin with. So this is where I'd suggest, was it that video series from 3 Blue 1 Brown with the neural networks? Just thumbs up, has everyone seen that part? Maybe some sideways, maybe some of it. Okay, that's okay. I would say after this thing, if you haven't seen it yet, go watch it. I think it does a really great job of explaining visually. And I say explaining visually, meaning that like it's not like dumbing it down. In some ways, you are kind of dumbing it to kind of summarize it, but I don't think he makes it so conceptual that you can't get much out of it. But he doesn't make it so like unattainable from like the mathematics standpoint, because sometimes it's just written with a bunch of partial derivatives for like stuff. And I think he does a good job of doing a good balance. So highly recommend that. If you guys need that thing, just let me know and I'll send the message out again. I think it was from like last week I shared. But okay, but today we're going to continue on back into, what's it called? Oops, I clicked the wrong one here. Into neural networks, and we're going to specifically go into more of the tuning optimization. So let me go and share my screen. And okay, so you guys should see my deep learning. And grab your window. Okay, sorry, I have to always reorganize these windows so I can see you guys react and everything. Oops. There we go. Okay, so remember this is just all on the repo, right, that we have. So I'm gonna go to neural networks. So past few times we talked about basically what a neural network is. We talked about activation functions, how that is part of the neural network itself. And then we also talked about, I think last time, correct me if I'm wrong, we talked about avoiding overfitting. Is that, give me a nod if you guys remember talking about that from last time, avoiding overfitting. I don't see anyone nodding, so maybe not. So we'll maybe look at that and see. So this is where we talked about like the train test validation, which we talked about before. We talked about the complexity graph. Is this looking familiar now? People? Okay, I think I see. So, okay, I see nods now. Cool. Sorry, some videos went offline. I wasn't sure if that was people or on my end. So yeah, we talked a little bit about like ways to avoid overfitting, because a big part of neural networks are really awesome. The real reason why they're really, really awesome is that they can find really complex patterns. And if you can find complex patterns in something that's a complex data, that's really awesome. However, when we have something that's very, very complex, right, or a model architecture, a machine learning algorithm, think of like the hyperparameters from like the other ML stuff we learned in Mod 5. But when our machine learning model, in this case neural networks, is very complex, is that it's more likely to overfit, or we're in danger of overfitting, right? So one thing we want to do is make sure we avoid those parts. So one way we can do this with especially neural networks is essentially every epoch, every run through, every like little step. So remember an epoch is its feed forward part, where basically it feeds the information, what's it called? The inputs, right? From the input layer going through the hidden layers and then to the output. That's the feed forward part. And then the back propagation part, we basically say, okay, how bad, like from its predictions on the output, what were the true outputs? How off were you? And then says, okay, you were off by this much. And back propagation says, okay, we should adjust the weights of the hidden layers all the way through back to the input layer. And basically you propagate that error backwards, back propagation. You propagate that error backwards, adjusting the weights ever so slightly. And that full cycle of going feed forward, back propagation is one epoch. So basically over every epoch, you should be getting better and better and better, because the idea there is we're doing gradient descent. Gradient descent is deciding how we're tweaking each of those weights as we do the back propagation part. So you can see in this blue here, you can see the error decrease lower and lower. And this is just made up data, but that's just like generally what you would see. And you would see the data go smaller and smaller and smaller. However, you should expect your validation error not to be as low, right? Because validation data set has not been seen yet. Your validation error is calculated. Does anyone remember how is this validation? Let's say we do one feed forward, one epoch, right? We feed forward, do back propagation. How do we find our validation error with the validation tests? Any idea? So I'll kind of make a little quick neural network. This is a very simple one, right? You guys will get the point. Okay, so what we have here, let's say this is the input. This is like a hidden layer. And this is like our output right here. Okay, output out. Okay, so what we normally would do, the way we train it is we take, let's say this training data, we put our training data, feed it forward, right? These weights already have some numbers. We feed it forward, and you're like, okay, cool. Like we get some prediction. Then we say, all right, compare. So we compare our prediction, right, with the true output. So we know what the output actually should be. It's like, okay, well, you did, you got these wrong, right? Or like you weren't close, right? And then we basically back propagate, changing the weights, propagating all the way back to the beginning, okay? And then we basically have trained our network to be a little bit better. When we get our validation data, which remember, we're not training with the validation, but what we do is basically saying, well, how well did our neural network do? And the way you do that is like, okay, we take our validation data set, I'll draw it in pink here up on top here, is that we just feed it forward. So we have a bunch of inputs, right? The features, we get some output predictions, so predictions. And then what we do, we just say, okay, how bad were our predictions, or how good were our predictions compared to what truly was that we should have gotten. And that gives us our validation error. And that's why our validation error is not going to be as good as our training error, because basically this neural network should do better and better on the training error, but not necessarily better on the validation. So what happens here is that you'll tend to see is that validation error will kind of go down, maybe not as quickly or maybe not as far down as the training error. And then what we want to avoid is something where it basically starts going up like this. And note that on the x-axis here is basically number of epochs. So we're going it over and over and over again. Basically, it's getting better and better and better and better. Okay. So what we want to do basically is if we see this, we're like, hey, that's overfitting, right? Basically, it's getting, the training error is getting better and better and better, which means the machine learning is learning, but it's basically starting to get better at the training error, but not generalizing it. So essentially what happens here is that we're actually getting, finding patterns that don't actually exist in the general data set. And we start this bouncing up. So I mentioned before is early stopping. Give me a thumbs up if you guys remember people for the last time, early stopping. I don't see anyone giving me a thumbs up. So I think no. So early stopping was basically, this is where I think the curriculum is something a little bit different. The curriculum says, okay, well, clearly we were overfitting at this point. We're making it too complicated. So we need to stop like at the 100th epoch, right? Instead of going all the way to 300 epochs or epochs, right? So one way you can do this, the curriculum says, all right, we know it's 100, let's go ahead and retrain it, but we'll stop at 100. In general, that is not a common practice, just because you can imagine it's kind of a waste of time. Is that imagine trying to train it all the way here and then you got to train it all over again. Or if you train it all the way to here, it's like, well, we just spent like, let's say a whole hour just trying to go from here to here. Maybe it figured out in the first like 50 epochs, but you trained it for like 5,000. Like, well, that was a huge waste of time. You should have just stopped it right then. Because, you know, if you could graph at the same time, you would see this go up. So there's two strategies to do this. One, well, they're both early stopping, but one, the idea here is that you just keep the model that has the best. So based on like, you know, some metric, in this case, the validation error. So you can basically save the actual model as like a file essentially. And that way you can run the whole thing and it'll go through however many epochs you're going through and it'll just keep that specific model at the very end, right? That's really nice. Note that this can also be done where you, instead of saving best only, you can actually save multiple models. So maybe as it gets better and better, you can actually keep multiple models. And that can be useful if you want to kind of like see how well this model, like where did it mess up? Like why was it the error not doing very good? You can do that as well. Another option for kind of like early stopping is really called early stopping with Keras. And basically the idea here is instead of kind of keep going, like imagine we just spent 200 epochs of basically just a waste of time. We should have stopped right here because the error pretty much stopped improving and started going up. You can actually say, okay, if the error basically doesn't change, the validation error, or the error doesn't, or the error kind of increases, right? Over so many epochs. So maybe, for example, there's just a random epoch that's like, it bounces up a little bit too high. It's like, okay, like if it doesn't change over like 5 epochs or 10 epochs or, you know, 1 epoch, whatever you want to do, go ahead and stop there. And that way we're not wasting our time training something that's going to overfit. And that's what this is right here, this early stopping. So the same idea here is basically this will go for 100 epochs unless this case is like 5, patients is 5, min delta is 0.01, monitors the validation losses, basically tells us what to watch. It will try to go for 100 epochs, but if for 5 epochs, the validation loss doesn't change by at least 0.01, then it's just gonna stop there. So at the 50th epoch, if the validation hasn't really changed that much, at least this is the delta we're looking for 5 epochs, it'll just stop it. It's like, okay, at the 55 epoch, it goes, you're not changing anything anymore, so we're just gonna stop the model right here. And this way you can avoid wasting extra time when you're basically just overfitting. Okay, cool, makes sense? Cool, no questions, right? All right, and I don't know if people who were here last time, if you guys saw this, so if not, or if you did, it's review. So this is where I mentioned about, I think we did talk about this then, good models and bad model, or when a good model goes bad. One way we can do this basically is through regularization, right? And the way regularization really works is basically saying, hey, like the reason why we're doing this, L1, L2, think ridge and lasso regression, right? These things are saying, hey, like the weights are too large, it's dominating over everything else. It's basically when we have large weights, we mean the model's too confident. It thinks it knows what it's doing. It's, oh, I got this easily. Or you have weights that are closer to 0 that are smaller. And I say smaller in the absolute value sense, so that when they're smaller, it's less certain. It doesn't know for sure exactly like how strong this is. Remember, our weights are going to represent saying how much contribution each neuron should have to the next layer. So regularization basically says, if your weights are too big, we're going to punish you, basically saying you're too confident. We need you to really ease up a little bit. So we talked about L1 and L2 regularization. So absolute value. So these are like ridge and lasso regression, right? And we talked about L1, which we've seen this before. Note that this J is our cost function right here. And hopefully, I mean, this probably looks really intimidating by itself. I don't know if you guys like how you guys feel about this, but this right here is all it's doing is it's cost function, and the cost function is based on the weights and the biases, right? So we feed its weights and biases into model and say, okay, how well overall on average, essentially, did the model perform? Did the model predict things well or not, right? And this loss function here, it goes through each of the data points, 1 through m. This L right here represents the loss function. Y hat is the prediction, right, based on the model. And Y, so it's Y hat I, so it's that specific, what's it called? Specific data point. YI is the actual true, like that's what it should have been labeled as, okay? And it says this loss function, you can define it however you want to basically say, this loss function says, how bad was our prediction, Y hat, from the actual Y, okay? And then normally that would be it, right? We just basically try to minimize this cost function and just sum it over. However, we add basically our regularization term. Note this is lambda right here. So lambda is kind of like this factor of like how much do we regularize it, right? The larger lambda is, the more it'll be regularized. And then we have our weights right here. So these are the weights for each of those data points, basically. And know that basically, if you're really, really confident in this case, we're actually going to punish you overall. Because remember, we're trying to minimize this cost function. And this WI right here, if this number is very, very big, it means it's going to automatically make this cost function larger too. which means basically it's like, oh, like I don't like that. It wants to minimize that. So it'll try to, like, if it can't do the loss function, what it might try doing, it'll try to optimize and say, let me go ahead and make the WI smaller. Okay, does that make sense to everyone, right? Cool. And L2 regularization, right? Basically, instead of using absolute value, instead we use squared value, and you can see it right here. Okay. In general, we'll use L2 regularization. This tends to give better results. Also, is that this will tend to make it more homogeneous. So the weights will tend to be more equal. So I gave an analogy of like 0.5, like if you had two vectors of like weights, 0.5 and 0.5 and 1, 1, 0. L2 will prefer 0.5 and 0.5 because they're close together versus 1, 0. L1 will tend to get rid of weights, will tend to prefer one weight or one of the weights over the other one. So it'll tend to prefer 1, 0. And this is kind of nice in some cases where if you want to get sparse vectors. So if you want these you want some of the weights to go close to 0. L2, your weights don't tend to go to 0. They might get small, but they won't get to 0 and they won't go away. Okay, cool. Everyone understand so far? Any questions, follow-up concerns? No? Okay, cool. So this leads us to something I know we didn't talk about this last time, which is dropout. So dropout is going to be another strategy for us to deal with overfitting, right? So dropout, this is kind of like my scenario is that if you imagine like if you were to like go to the gym every day and like, you know, use the same arm every day, or like, you know, you don't switch between legs and arms and stuff like that, right? What you'll have, especially like with one arm here, is that essentially you'll have one arm that's much stronger than the other one, right? Which, you know, that's great. You have a strong arm, but you know you're not really equaled out, right? You basically have a weak end over on this side. So this is actually really true with neural networks too. Is that neural networks can do the same thing, where it'll tend to prefer certain neurons over other ones. So what will happen is the value of the neuron, or sorry, I should say the weight of the neuron connected to those neurons, will tend to get very, very large, and then the other sides will get smaller. And what might happen then, if you imagine, like if I quickly draw out a little neural network here, I'm just gonna draw it in some dark color so I can actually see it well. So if we have like a neural network like this, let's see here. I'm gonna put 3 like this. Okay, I connected everything. Oh, I didn't connect this guy. This one. Okay, so the thing is that let's say, for example, all of these weights go to 0, right? Or let's say the weights to this one goes to 0 or very small. This neuron is going to be very, very weak. So what's going to happen then if I have like another hidden layer and it would connect to, let's say, these two guys again? What's going to happen is that this is effectively this neuron right here. Okay, this is 0. This is this part right here is going close to 0. This part's going close to 0, and this one's going close to 0. Where the point, like basically, no matter what number you feed into here, this is always going to be close to 0. So this neuron, we call it like a dead neuron. Essentially, it's not being used anymore, and basically everything is going to this single neuron, right? So the problem with this is that basically it's preferring over any other one on this specific neuron, and this neuron's going to do all the work, which might be fine, but the problem is now you're overfitting. You want more complexity. You want it to be less certain. You want to try out the full architecture of this. So you want to avoid it to kill off this neuron, or we call them like dead neurons. Is basically this neuron now, no matter what, because it's going to be close to 0, these paths will always be close to 0, so it'll never really contribute. So this architecture you had originally that looked like, you know, 3, 2, 2 might end up essentially looking effectively like 3, 1, and then 2. And you can see that's a very different architecture going forward. We want more complexity. Remember, the whole point of neural networks is that we want that complexity to find that patterns. So what we can do is, you know, just kind of like in the scenario of like, you know, if you exercise one arm over the other one, right? What you would do is you switch up arms, right? So in neural networks, we can kind of do the same thing. Is like, instead of saying, okay, train with all the neurons every single time, instead what we do, we can say, all right, let's go ahead and sometimes not use that neuron. And that way it gets full practice. So you get practice from left and right kind of deal. Or in this case, all the different neurons. Note too that I only drew 2 neurons, but imagine if you had like a very complicated set, right? And you're like, okay, I need a very complicated neural network architecture. And you have, you know, many, you know, neurons in a layer, but then most of them go away. Well, now you don't have a complicated neural network, right? And they're like, oh, that's a lot more, it's way too simple. So that's the reason why we want to use Dropout. So let's see here if I can show you. You're putting stuff for and training. So the way we do this essentially is we take a neural network, right? So imagine this neural network here that I kind of have a picture of. And what we're going to do, we're basically going to switch it up where we're not going to use the same neural network or neurons every single time. So essentially what we do, we assign a probability for each given node, each neuron. And basically on every epoch, we say, okay, you have a 20% chance, that's a typical number, 20% chance that you'll actually be used for this training, right? This epoch. And so we go each one basically flip a coin, or you can roll a die or whatever you want to think of it as, right? And basically say, are you going to be used for this, round or not? Yes or no? And if there's a 20% chance in this case, we say, okay, well, you're going to go ahead and use. So let's say we roll our die, or, decide, right, with 20%, it's like, oh, yep, we're going to go ahead and use you. And then we roll our dice like, oh, we're not going to use you this round. And then we go through here, it's like, oh, are you going to use you? Oh, yeah, we're going to use you. Oh, yeah, we're going to use you. And then we go for each node. It's like, okay, are you going to be used? No, you're not going to be used here. Oh, no, you're not going to be used here. You're going to be used. You're going to be used. And what this does now is that we do this every epoch. So we check it all that through. And then we say, okay, go ahead now, train it. So now we feed the data forward and we do back propagation. And the backward propagation is only going to affect these weights right here, the weights that were used for that neural network. Okay. And then the next round is like, okay, we go ahead and get rid of them. And we say, okay, we try again. It's like, are you going to be used? Yeah, we're going to use you. Are we going to use you? Oh, no, it turns out we're not going to use you. Are we going to use you? No, we're not going to use you this time. Are we going to use you? Yeah, we're going to use you. Oh, yeah, we're going to use you. We're going to use you. Oh, we don't, just randomly kind of picking, right? And so obviously sometimes neurons will not be used multiple rounds in a row, but that's okay. It's all random, right? And so I actually had I've heard this really great kind of analogy to this, is that it's kind of like, if you imagine each neuron being like a worker in a company and your neural network is the company, imagine if you just randomly at work, throughout the work week, someone that you're just randomly chosen if you're going to go to work today or not. Well, you can imagine that you can't have a person who's going to be the only person who knows how to do that thing, right? The company wouldn't do very well. So the company might have to essentially end up doing, it's like, okay, well, we can send anyone home, randomly for the day. Then we need to make sure that everyone kind of knows. They have to generalize a little bit more. They can't just cover just one thing. They have to cover multiple things. And the idea there is maybe, for example, I don't know if this would work in practice, but the idea is you would have everyone be a little more generalized, right? And that way, if someone were to leave, or let's say someone got fired or something like that, you would have a better chance of not having it to be so much of an issue. And that's kind of what the neural network is doing. Another way you can think about this is that you're effectively making a new neural network, new neural network architecture every time you do a dropout, every time you do an epoch. So essentially what you're doing, you're saying, okay, I'm going to train a network that looks kind of like this. So I don't know if you guys, how easy that is kind of to see from in red. But if I were to say, okay, this is the neural network going through here, and then these are going to connect to here, and these ones are going to connect to here. And so essentially what it is that we're going to make a new neural network essentially every single epoch. And then at the end, essentially we're kind of averaging them as we go through of different neural network architectures. And you can see that would also generalize really well. Okay, does that make sense to everyone? Cool. Okay, thumbs up, thumbs down, sideways. Okay, see some thumbs up, some sideways. Okay, cool. All right, so example code, how do you actually implement this? Turns out it's actually really easy with Keras. So we already knew how to write in Keras, use our, write our neural networks, right? So we still use sequential. We have our dense layer, which is basically going to be our layer by our inputs, our hidden layers, and then our outputs, right? And then we're going to add this new thing called dropout. So all you have to do, essentially, you can think of having your input layer. So you can see here, I have an input dimension of 100, and then I have my first layer. So you can imagine this is going to be 100 elements. The next one's going to be 128. And then what we do, we can just add a dropout layer right here. So you can basically say, okay, this layer right here, there's going to have a dropout layer. Essentially, it just kind of connects to this first layer. And you say, okay, there's a 20% chance that a neuron will not be used this round, going through. And that's what this dropout is right here. Then we have our next layer. You can see here, 256. So you can imagine like this next hidden layer will have 256. I don't know why I have input dim. This should not be here. Oops. There we go. All right, so you have now 256 would be like the next layer, and then we actually say, okay, that layer will also have a dropout, saying that each neuron in that layer will have 20%. Note that I could technically change this to like 30% or something like that. The numbers themselves are relatively arbitrary. It doesn't have to be those numbers, though. Know that for neural networks, usually 20% does pretty well. And then for convolutional neural networks, turns out 40% or even 50% actually does even better for convolution, which we haven't talked about yet, but from our image recognition. Also note that dropout, remember that we can have like many, many hidden layers, right? So we can have many of these hidden layers. In general, dropout only needs to be done for the first 3 to 4 layers. If you have a very deep neural network where you have like 6, 7, you know, however many hidden layers, you usually only need dropout for the first 3 or 4 layers, because basically by the time it gets to those end parts, you're already getting more complicated, what's it called? More complicated patterns. At the beginning, it's really easy for it to basically try to find a really easy, like, you know, lazy way, not finding real patterns, and it'll go through that direction. So that's why in general, for deep neural networks, you only see dropout for the first like 3 or 4 layers. Okay, and you can see if I run this now, you can see the model summary. Eventually, there we go. There we go. All my warnings. Yeah. Okay, there we go. So you can see our model right here, and you can see our summary. We see our input. Our input was 100. Then we have a layer of dense of 128. Our dropout, and then our hidden layer again, 256. I shouldn't have here. This really should be hidden layer. That's okay. And then you can see here another dropout, and then our output. Okay. All right. Any questions at all? No? Sound pretty good? All right. So that is all the stuff I want to show you really for overfitting. Dropout, again, is typically really used. There is some research, you know, people say like, you know, should use dropout or not. Note that dropout does mean that you might have to take longer for it to train, because now you're purposely crippling your neural network, but in the hopes that it's not going to get too confident. It's not going to be overfitting. Okay.